been talking about sampling distributions and how we can use those to answer questions, basically about proportions so far. We're going to talk about means tomorrow. But basically, it's like if somebody makes a claim that a proportion of something does something, we want to test and see if that's valid, okay, if that's significant. Okay? Or if, sorry, not significant, true or false. So what we did in the last class is we set it up like a normal distribution. So we found the mean of the sampling distribution, which is the same as the mean of the population distribution. We found the standard deviation using a certain formula that you will always get, okay? And then we use that along with the normal distribution to answer the question we wanted to. Now, in order to say that the mean of the sampling distribution is the same as the mean of the population distribution, a certain condition has to be met. In order to use the standard deviation formula, a certain condition has to be met. In order to say that it's a normal distribution and we can use our normal CDF calculations, a certain condition has to be met. And that's what we're going to talk about today. So here's the example for today, polls. Okay, and this goes back to 2016 in the States, where very close to election day, there was a very high percentage that Hillary Clinton was going to win. And yet we know what happened. Okay. One might even say that it happened again, maybe not to a lesser extent, this past November, where there were polls out there that saying Kamala Harris was going to win, and yet Trump won, and he won rather decisively. Okay. There was one way back in 1948 where newspapers printed that a certain guy beat Harry Truman, and Harry Truman won the election. So they had printed all their newspapers because they got their polls wrong. Right? So what makes polls mess up? Well, here we're going to look at the state of Wisconsin. Okay? And what happened was, in the end, 60% of Wisconsin's major party voters voted for Trump. Okay? So we would expect Trump to win, or sorry, Trump won this. However, the polls didn't say that. Polls said, and these are kind of hard to read, there were a whole bunch of polls done here in Wisconsin where Clinton was winning a lot of them. And Trump, I mean, I think, actually, I don't know if it's all of them, but there was, yeah, I think maybe these polls had her winning all of them, yet in the end, it was 60% Donald. So in a world where 60% actually voted for Donald Trump, we're going to take a random sample of 30 voters, and we could get the following results if it's going to center around 60%. Maybe we get one where 17 out of 30 voted for Trump. Out of 30 voted for Trump, which is approximately 0.57, 57%. And maybe 18 out of 30 for Trump, which actually works out to exactly 60%, or 0.60. And maybe 19 out of 30 voted for Trump, which works out to about 0.53. Wait a minute. That's wrong. What am I getting there? Did I reverse those? I must have reversed them. 17 out of 30 makes more sense to be 53%. Or 19 out of 30. Sorry, 19 out of 30 is 63, not 53. So if we took several samples, okay, they would center around 60%. That's what normally happens, okay? And the sampling method that we used, okay, or was the sampling method biased or unbiased? It was unbiased. Because the proportion voted for Trump centered around 60%. So you can see, and that's what happens when we have an unbiased estimator, like a sample proportion. I mean, we could get a sample proportion that's quite high, we could get one that's quite low that sort of cancels it out, but the majority will sort of center around 60%. And what's the key? And this is the first condition. What's the key to obtaining an unbiased estimator that allows us to say the sampling distribution is the same as this? Random. It must be a random sample. Because if it is not, we're going to get a different distribution, not centered around 60%. So it must be a random sample. If it isn't, we can't say that the mean of all the sample proportions is the same as the population proportion. We can't say that. And then we can't answer a question that we want to. And that's really what happened in the States, in quite a few of the states, where they were saying, oh yeah, Hillary's going to blow them away, Hillary's going to blow them away, but then Trump ended up winning. Okay? Is what happened is really the samples that they took, even though they said they were random, were really not random. So what you ended up with is you ended up with a distribution that was lower than what actually happened, right? Because he would have received a lower percent of the votes, so the sample ones would have been centered around that, okay? So based on that, this is biased. The polls were biased because they underestimated. Remember, when we talk about bias, we talk about over and underestimated. They underestimated the support for Trump. And how did they do that? Well, we'll see in a second. So like I said, the first condition, the random condition. So you must ensure that the sample was randomly selected from the target population. Randomly selected. From the target population. And if the condition is not satisfied, the estimator, in this case sample proportion, is biased. And it's not going to give us an accurate result. So here's basically what they figure happened in Wisconsin. Okay, voters without college degrees had a very low response rate in the polls. So they were underrepresented, and the majority of them voted for Trump. So they missed them all. And undecided voters at the time of the election broke more towards Trump. So a combination of those two things allowed Trump to win, but suggested that Hillary was going to win. So how do each of these above represent a violation of the random condition? Well, you're not randomly sampling the whole population. That's a violation. Not randomly sampling. If you're going to miss a whole group of people, that's not a random sample. And really, same for this. Not randomly sampling. The whole population. You're missing these groups. And as a result of missing these groups, you're missing what actually happened. So that's an example where it stresses the importance that it must be random if we're going to answer questions like this. The second condition, and this condition allows us to use the standard deviation formula, and it's called the 10% condition. Okay. So remember in the last lesson, we could calculate the standard deviation of the sampling distribution, standard deviation of the sampling distribution. Remember, whenever you talk about sample distribution or sample proportion, use hat over P is equal to the square root of the proportion of the population times 1 minus the proportion of the population divided by your sample size. So in that previous example, or sorry, the example from the first page, remember we said 60% voted for Trump, so we take 0.6 times 1 minus 0.6, and we had a sample size of 30 we took. And when you calculate that, you're going to get approximately 9%, 0.09. So what does that mean? Because we're asked to interpret. Polls will typically vary, because we use that phrase for standard deviation. Make sure I get this right. From the true proportion that voted for Trump, the true proportion by, you could say 0.09 or 9%. So that's the spread. In order to use this formula, like I said, and this is the 10% condition, the sample size that you take must be less than 10% of the population size you're drawing from. In other words, sample size is represented by little n, population size is represented by capital N, so little n is less than 0.10 times capital N. Okay? And it assures us, or it allows us to use this formula. And it's really about independence. Okay? That's what the 10% condition comes down to, is testing independence. Because if you don't have, if your sample size is not less than 10%, your probabilities are going to change drastically, which means we're not going to get an accurate result. So just as an example, and this is sort of the intuition behind 10%. Let's say we're taking 3 individuals from a population of 10 that voted Republican. So we want to find the probability. Well, this is how we would do it. To find the probability that we found all 3 Republicans, 60% for the first one times, and the second one is times, and the third one is times. So you get 0.216 for probability of randomly selecting with replacement. So what that means is you select an individual and then you put that individual back in the population, and then you select again, and then that individual goes back in, and then you select again. Okay. These are independent events. Previous outcome does not affect next outcome. So that's like flipping points. Because we put that person back into the population, the probability stays the same. So it's not going to influence the second probability, and it's not going to influence the third probability. But that's not what happens in real life. Okay? Especially like if you're surveying people in a mall or something like that. I mean, you're not going to grab the first person that you see, ask them who they support, and then say, okay, go back in and wander around the mall because I might randomly select you again. Yeah, it doesn't make sense. Okay, so what really happens a lot of times is without replacements. And we saw that before when we did the probability unit. So the probability of selecting the first Republican, or the first person that supports Republican, is 6 out of 10. However, that person is not put back into the pool. And we've already selected one who is Republican. So the probability of selecting a second Republican, well, there's only 5 now out of 9. Because we already selected a Republican, so it's 1 less than 6. And that person did not go back into the pool. So there's only 9 left in the pool. So the third one is going to be 4 out of 8. This is what normally happens. And if you multiply those together, you're going to get approximately 0.167. These are dependent. where previous outcome affects the next outcome. Notice those two probabilities are significantly different. Okay. But we want our sampling to be independent. Not only do we want it to be random, we want it to be independent. So if we're choosing 3 from 10, that means 30%. We're choosing 30% of the population as our sample size, which is well over the 10% condition. You can see that it becomes dependent instead of independent, which we want. So what happens if we keep the sample size as 3, but the population size increases? In other words, the sample size is going to be a less percentage, less than 10% of the population. So let's say we have 640 people. Well, the first one, 6 out of 340, sorry, that's wrong. 340? No, 640. So what's the probability of getting a Republican on the first one? Well, it's 60%, right? So how many out of 640? Well, this has got to work out to 60%. So it's 384. That's the probability of getting a Republican. That's 60%. So 384 of those 640 will support Republican. We've already picked one, which means there's only 383 left out of a total of 639. And then we do the second one, and then moving on to the third one, there's, assuming we selected a Republican again, there's only 382 left out of a total of 638. Well, when we calculate this, we're going to get approximately 0.25, which, if we notice, is very close to when it's independent. So if our sample, so what that means is if our sample size is less than 10% of the population, these results will be very similar, whether it's, I mean, technically this is dependent, but its probability is very, very close to if it was independent. So that's sort of the reasoning behind it. Oh. So if the sample size n is small, under 10%, compared to the population size, capital N, process is almost independent, virtually independent, which is what we want. So if that condition is satisfied, we've got independence, which allows us to use that standard deviation formula. So we've got the mean, of the sampling distribution. We've got the standard deviation. We just have to assume that it's normal now. So we have to meet the third condition, something called the large counts. Meaning your successes and failures, okay? So your sample size times the probability of getting what you want is your success. Your failure is your sample size times the probability of not getting what you want, or 1 minus p. And both of those must be greater than or equal to 10. Okay? If it's not, you're not going to get a normal distribution. And I'll explain that in a second. So the sample size times the probability, or times the proportion of probability. Must be greater than or equal to 10. And that's a success. That means, like, remember, in our previous example, the sample proportion was 60%. So a success was getting a Republican. A failure was not getting a Republican. And how do we calculate a failure? Well, it's the sample size times 1 minus the probability of getting the success. That also has to be greater than or equal to 10. And if those are met, we can say that the distribution is approximately normal. Which allows us to do normal calculations to answer these questions. So here you can just see what happens in a large counts, and why we need the large counts condition. So in the first example, we have a sample size of 8, but the proportion is really small. It's 0.05, 5%. Okay? So you can kind of see what the distribution looks like with a small sample size. It's not normal. It's kind of half. Okay? That's what would happen if we had a small sample size and an extreme proportion. Okay? So it would be, because remember, we can't go into negative. You can't have a negative proportion. So we say, like, it's close to the edge, which is 0. Remember, we did talk about the higher the sample size, the lower the variation, the lower the spread. So because it's a low sample size, it'll have a higher spread. And as a result of these two things, it's going to be not normal. In other words, we can't do normal calculations. But what if we had still the same low proportion, which will again be close to the edge, close to 0. But we had a much bigger sample size. Remember, the sample size squeezes the spread. Less variation. And because it's less variation, because it's tighter, we do actually get a normal distribution, or approximate.
Two things.
If we have a lower sample size, which is going to give us higher variation, but the proportion was not extreme, okay, we will get an approximately normal distribution.
So non-extreme P means, how did I say this? Yeah. Say not this edge, this is 0. The low sample size means higher variation. But because the population proportion wasn't extreme, we're again in an approximately normal situation. Sometimes you will come across a question where you are told in the question it is approximately normal. And you don't have to test this condition. You just, well, I mean, you say the condition is met because you're told that it is normal. So just as a summary, and this is a good thing to refer to. When I'm dealing with a sample distribution of a proportion, it will be normal as long as the large count condition is met. Okay? So it will be approximately normal shape. If the sample was selected randomly, that means I can say the average of the sampling distribution will be the same as the average of the sampling distribution of sample proportions will be the same as the true population proportion. So it will be an unbiased center. And if the 10% condition is met, that means I can use that formula. It's got a calculable spread. So when you come across a question like the ones we did in the last lesson, we assumed the conditions were met, but now you're going to have to check these conditions as part of your solution. So just going back to the example we've been using in this lesson, okay? We want to check the conditions. So in a world where 60% of all students at your school are Republican, the true proportion is 60%, you randomly poll 30 students to find the proportion, the sample proportion that are Republican. So first of all, and this is how you would just say, random. Random condition is met because 30 students were randomly selected. 10% condition. Sometimes we're going to have to assume. So in this case, we are going to assume that the 30 students we selected are less than 10% of all students at the school. So which means there would be at least 300 students in the school. Usually what will happen if you get one where it's a school, it'll say large school. And large school means like you usually assume at least 1,000. Okay. So that allows us to use the standard deviation formula. And finally, the large counts. See whether it's actually a normal distribution or approximately normal. Sample size times the true proportion, which is going to be 30 times 0.6, which is 18, which is greater than or equal to 10. That's good. That's successes. Failures also has to be greater than or equal to 10. So 30 times 1 minus 0.6 or 0.4 gives us 12. Gives us 12, which is also greater than 10. So we've met
All the conditions. Which means basically we can go ahead and answer the question that we're being posed. Because the conditions. So
to describe the sampling distribution, because it also asks for that, you would just say sampling distribution is normal with the mean of the sample proportions equal to the, sorry, the mean of the sample proportions equal to the true proportion, which was 0.6, and the standard deviation of the sampling distribution. We can use that formula 0.6 times 1 minus 0.6 divided by 30.
which gave us approximately, what was it again? 0.09. And then what happens after that is, you know, you're given a sample proportion, or you're given the true proportion. And then you're asked, okay, like in our sample, we got 55% that supported Republican. What's the probability of getting 55% or even lower? And if that's a really small amount, then we have convincing evidence that the actual proportion is less than 60. If that's not a small probability, then we could have got that result by chance alone. And therefore, 60% is the true proportion. Okay. Any questions? I made up an example one. No, I'm not. I've got to print it out, but we'll do it tomorrow. We'll do it tomorrow morning before we do 6.4. Yeah. Okay. So